Hello, welcome to lecture 30. In the previous lecture, we discussed wave kinematics and we saw how superposition of two waves of slightly different wave numbers can lead to formation of a group of waves, and we derived what is the group velocity, and that is important for us as we go along in understanding internal wave structure. So in this lecture, we will discuss internal wave structure. So as we discussed above, we can always rotate the coordinate um, system for the internal waves to lie only on a certain plane of interest. So as I discussed earlier also, again this is a brief recap. So we have a wave vector, and this is this is the direction that we see as the wave traveling, and this is something which is physical. This is something that we as an observer observe, and because we are scientists and engineers and we need to analyze that the travel of the wave, we have created a certain system which is a coordinate system, an orthogonal system, and we say that this helps us in our calculation, and this is where we'll put this coordinate system. And this is the vector, wave number vector. The wave number vector does not care about how we assign the coordinate system. But now, to make our calculations simplified, we rotate the coordinate system in a sense that the wave number vector now lies in the xz plane, that is only in one plane, and nothing changes in the other direction, that is the, let's say this is the y direction, and nothing changes along the y direction. And we have the full freedom to do this because we created this coordinate system, and we can rotate it in any way that we want. So we have done this, and hence the vertical velocity, or rather the y component of the velocity is 0. The vertical velocity is not 0. Vertical meaning, in this case, we are taking it to be the z direction. So we choose w of a certain form. It's a cosine function. Given the fact that we have unbounded domains, we can choose a form like this. And from incompressibility, so if you recall, we had written down the governing equations, and we had substituted some assumed solution, and we got a form of the equations from in terms of, these are algebraic equations that we derived, and we recall that from there we have I kxu plus I kzw is equal to 0, given that v is 0. Due to our choice. So v is 0 due to our choice of axis. So this gives us u as minus kz by kx times w, which is w naught cos of this argument. Now similarly, from the set of equations that we have derived, also get the forms of p prime and rho prime. So in terms of w, we derive the governing set of equations by plugging in the assumed solution, and we can get p prime and rho prime in terms of w, and we'll see that rho prime, and this is left as an exercise for you. So this is, we'll find that rho prime is out of phase with w. Okay, and then we will have a set of equations where we find relationship of the governing or of the variables in the problem in terms of a certain variable that we have defined here. This is We have defined W here, and we'll find other variables in terms of W. So in wave mechanics, such algebraic relationships between amplitudes and phase of different physical variables are called polarization relationships. So these are relationship between different variables um, governing the wave dynamics. And some of these, these exploring or getting the relationships of p prime and rho prime is left as an exercise. We will do most derivations, most intermediate steps, but some will also be left as an exercise. And this is where your work starts. This is what you can create, and you will find that and convince yourself that this rho prime is out of phase with W. This is something that I have written, and you can convince yourself. The u and v velocities have opposite signs, meaning when one is at its maximum, the other is at its minimum. So this is what we get from this relationship. Now, for internal waves, the lines of constant phase that is lines of constant trough or crest tilt perpendicularly to the wave number vector. Okay. The lines of constant phase tilt perpendicularly to the wave number vector. Okay. So why is that? Why is that so? We can do this. Just calculate k dot u. Okay. So we have kx minus kz by kx w plus kzw, which is equal to 0. And where do we get this? It's from the first polarization relation. U in terms of w, and hence when we do k dot du, this wave number vector times the velocity vector, we see that they are perpendicular to each other. Drawing some schematics for better understanding. These are some waves, and this is a line of constant phase, let's say connecting all the troughs. And the wave number vector is kx comma kz, and this makes an angle theta to the to the horizontal. Makes an angle theta. So there's a line of constant phase. The solid line that I have drawn is a line of constant phase, and this is the direction of the phase velocity, and the direction which is perpendicular to the phase velocity is the direction of the group velocity, and this is the energy propagation direction. So internal waves are propagating towards the surface, assuming that the surface is up there, towards the surface at an angle theta to the horizontal, whereas the energy is propagating downwards along this line of constant phase. Internal waves are transverse waves. And this is a consequence of incompressibility. It's important for us to know. The direction of the phase velocity is perpendicular to the direction of the group velocity, that is the energy propagation. Okay. The polarization relationship that I said we have to create this p prime and rho prime give us that the density fluctuations are 90-degree out of phase with the velocities. So this means the velocities are zero at the trough and crests of the waves, because those are the points of maximum fluctuations in density. Okay, as you can see, I mean, we have a density variation, and the maximum changes in rho prime occurs in crest and troughs, because those are the regions which protrude into a different ambient. So these are regions of maximum changes in density. Because density is out of phase with velocity by 90-degree, so troughs and crests of the waves are locations of zero velocities, but their maximum at lambda by 4 or lambda by 4 distance. Let's say this one-fourth of the distance, one-fourth of the wavelength, the velocities are maximum. So we have a wave which is, let's say, the calculation of the crest, calculation of the wavelength is being done from here to here, and one-fourth, this is not a very perfect, let me draw this wave again. So this is one wavelength of the wave, so the velocities are minimum when at zero at these locations, whereas they are maximum at one-fourth the distance. So one-fourth are these one-fourth the wavelengths, one-fourth the wavelength. So that's a correct statement. So from dot A to dot B is half a wavelength, dot B to dot C is half a wavelength, but velocities are maximum in these distances because they are one-fourth the wavelength from the points in which velocities are zero. So this is a zero velocity point, this is a zero velocity point, this is the crest and this is a crest and the trough, whereas the other points A, B and C are positions where they are maximum. The propagation of the energy is given by the group velocity, as we saw in wave kinematics discussion. So we have the energy moving in the group velocity in the x direction is the speed at which energy is moving in the x direction, and x direction meaning the coordinate system that we have designed. Okay, so this is the component of the energy in the x coordinate direction, and this is equal to we have this Persian relation. This is just one step differentiation of the omega with respect to kx. Similarly, and this is also left as an exercise because it's a very preliminary calculation, a very easy calculation, and this one is omega kz okay. Now this this group velocity is perpendicular to the wave number, and is downward, as we drew in this schematic. The group velocity is downward. I mean, it's perpendicular to the wave number direction and it's downward. We skip the proof here. You can do a dot product of the wave number vector with the group velocity and see that for yourself, but we skip the proof that this is perpendicular to the wave number vector. But this is something that we must be aware of. Now, for a purely horizontal wave number, kz is equal to 0, theta is equal to 0, omega is equal to n, and c is equal to n by kx. That is the motion the group velocity, let's say um, the group velocity cgx equal to cgz is equal to 0, and energy does not travel. Why is it so? We just derived the form of the group velocity cgx and czz for a purely horizontal wave number, that is kz is equal to 0. There is no variation in the z direction of the wave. We have omega equal to n cos theta. The theta being 0 is just omega is equal to n, and c is n by kx squared, and the group velocity is cgx czz is equal to 0 from this expression, because we put kz equal to 0 in both of these, 1 and 2, rather these two terms, and this is equal to 0, and energy does not travel. When kx equal to 0, so this is one limiting case. When kx equal to 0, theta is equal to 90 degree and omega is equal to 0. So this implies a steady state or a frozen state. This is what we had seen earlier in geostrophic eddy. So we saw that we see that when kx equal to 0, there is no variation in the x direction. The wave number vector makes a angle of 90 degree, and this is a frozen state. It's a steady state. So that this means there is no wave propagation. Okay, so there is no wave propagation. So having discussed these limiting cases, let's go back again to the assumptions that we started with. We said that um, we will neglect the rotation term in deriving the basic form of the internal waves, and this was done for us to have a better grip on the system itself, to better understand the wave formation in a continuously stratified medium. And this, remember that this is a baroclinic process. Now let's introduce rotation. As we have said multiple times, rotation is important, stratification is important in geophysical flows. Hence, let's try to introduce rotation and see what happens. Introduce rotation and let's see. So the internal waves can be of lower frequencies to be affected by Earth's rotation. Also, also, we had initially assumed that the domain was infinite. We now have a situation, we consider a situation of finite depth. Consider a situation of finite depth, and this is important because we now uh, cannot have an unbounded wave in the finite depth direction, and you will see how that will come into the solution of the equations that we assume later. Okay, so if it's unbounded in the horizontal direction, we can have a sinusoidal form, whereas for the finite depth we will have certain different forms, and this will have to be derived. I mean, those forms of the wave in the vertical direction will have to be derived. So we consider a situation of finite depth, and we'll see the implication of this. So we have said that Earth's rotation is important, but we assume only an F-plane approximation. Please recall that F-plane is where the Coriolis parameter is assumed to be constant, whereas beta plane is where Coriolis parameter is considered to be varying with the meridional direction. So in most cases, almost all cases, we will always have uh, f squared less than n squared. This is always the case, and this is what we will keep in mind. This is just the common. So now, including rotation, the governing equations are these are the primitive equations, so del u del t, but remember that these are not barotropic, because formation of internal waves itself is a baroclinic process. Rho naught is some reference density. We have the three momentum equations in x, y, and z. and we have the continuity equation. From the above set of homogeneous, I mean these are set of homogeneous PDEs. What we can find is we will assume some solutions, and we will first, to assume those solutions, we'll have to first give an idea of the boundary conditions. So we utilize the fact that something, a flat bottom and a flat uh, surface is easier for us at this point. So we assume that the vertical direction is bounded but is also flat. There is no topographical variation, and surface is not a free surface. I mean, it's a rigid lid. Rigid lid and a flat bottom. So we will use separation of variable technique and assume solutions of the form to the above partial differential equations. The script f, there's a function in z, so this is the z direction, ux comma y e raised to minus I omega t. V, the some function of z, the script v, x comma y e raised to minus I omega t. And this is being done looking at the form of the governing equations and the boundary conditions, and this approximation of solution of this form will help us in getting to a slightly more clearer solution. So the form of rho prime is informed by the polarization relation. So we have assumed that the variables can be separated, and using these in the governing equation, these are assumed solutions, assume functional form of solutions. Using them in the governing equation, you just have to differentiate with respect to time and space. So this is not new, but this is script v minus I omega script v is equal to minus f u minus del script p del y, omega squared minus n squared script w minus del script f by del z, and 1 by p, 1 by script p del script u del x plus del v del y is equal to minus I omega script f. Okay, so these are arrived at by substituting the forms of the solutions that we have assumed. So the left hand side of the last of this equation does not depend on z, while the right hand side, so this left hand side is the right hand side, the right hand side does not depend on x and y. So the only way this is satisfied is if both the terms are constant. Again repeating, the left hand side does not depend on z, the right hand side does not depend on x and y, and it's the only way these are satisfied if both the terms are constant. So let this constant be I omega by GHE. It's quite an interesting constant for us to assume, but this is just we are assuming, and you will see this helps us in the calculation. And this is actually done with some information, background information, but let's assume that this is of this. I mean, this is the form of the constant, where He is some constant. Now using minus I f script d w del z, that is the right hand side of the last equation. So we'll this, given the fact that we can cancel omega from both the places, so there's omega here, and we have assumed this the constant or both these terms to be equal to this one, so we're equating first right hand side to this constant term, and this means dw by dz is equal to minus f by g he. So differentiating with respect to z, we have d squared script w by dz squared is equal to minus 1 by ghe df by dz. Okay. This gives a form of df by dz is equal to minus ghe d square script w by dz squared. Okay, so plugging this in the third governing equation, that is in the z momentum equation, into third governing equation, we have omega squared minus n squared script w equal to minus del script f by del z. Because we know that del f by del z is equal to this constant. Okay, this gives us the one that we have been, an equation that we have been chasing all along, and this is important because now we have an equation which is governing the vertical mode w script w. Once we have a solution to this equation, we can plug it here in this, and by polarization relation we will have the solutions to the other variables. So this is a vertical the equation for vertical mode. While I say mode, this is the form of the wave in the vertical direction. This is what I mean by mode. So what is the shape of the wave in vertical mode? How many nodes? How many how many crests? How many troughs are there? So this will give us an idea of what is the vertical structure. And with this, we can find the other velocity components. So once we have this one, we'll see how will find the u, v, and p, and we'll also calculate what happens to the. We'll also see what how the dispersion relation is modified in the next lecture. Thank you.